Now, kind of tied to this idea that water is the universal solvent, we have this idea of mixtures. All right, and there's two ways we can get mixtures. The first is going to be what's called homogeneous, which just means the same throughout. And we also call them solutions. Now, the way this works is if you have water acting as a solvent, that means it's what something is being dissolved into. Then you can add a solute to it, that's what you're dissolving into the solvent. And if it evenly distributes, if it makes it where if I take this first spoonful, it's the same as the last spoonful, we call it a homogeneous mixture, we call it a solution. So water makes lots and lots of solutions, and this is true of our body as well, where we can dissolve or dissociate things into the water, and then we can spread it throughout our body. You know, it basically just evenly mixes, it does not settle out, it's good indefinitely. Now, the other way you can mix things is you can have something called a heterogeneous mixture, which is uneven. So that would be like a salad where you can see it's not evenly mixed. It's not like everything is equally spread out. So if I go through and grab one scoopful, it's always going to be the same stuff every time. That's not true. You'll see in terms of water, we get heterogeneous mixtures when there's things that don't dissolve in water that are mixed. So for instance, sand and water. So if we talk about like lakes or rivers, we can talk about how it gets disturbed and you get all the silt and the dirt that kind of mixes up and makes that muddy water and eventually settles out elsewhere when you get a delta as it goes and slows down as it goes into like the ocean or something. Now the last general idea we have to get across here with water is going to be the idea of acids and bases. So we're going to take essentially a little bit of time here and get comfortable with that. Now really what an acid is it's something that releases H+, sometimes called a proton, hydrogen ion, something to that effect. Now this H+ can be reactive, so it can be a big deal how much of it we have. The more H+ we have, the more acidic something is, the more reactive it tends to be. Now bases tend to release a guy called OH- or hydroxide. Now hydroxide also can be reactive in high amounts. So if we have something that's very basic that releases lots of this, it can cause reactions to occur with molecules in our body, which we don't want, which can lead to things like chemical burns, or it can lead to our enzymes not working, which can lead to death. Same as acids can. Now the pH scale is how we measure how acidic or basic something is. And so what we're going to be doing is measuring the concentration of H+ ions. And the way this works is like a pH of 1 is effectively saying that our concentration is 10 to the negative 1 of H+, or essentially that we are 0.1 as far as H+, 10%. Now you can also have where you have a pH of 4. A pH of 4 would mean 10 to the negative 4th concentration, which if you go through and start moving your decimal, you're going to get 0.0001. So this is ultimately how we're going to calculate how acidic or basic something is. We're going to look at how much H+ it possesses by using this pH scale. But the pH scale, you have to realize, is logarithmic. And what that means is the difference between a pH of 10 to the, well, let's go through the difference between the pH of 3 and 6, as I've got down here, is actually going to be pretty significant. Because 3 is 10 to the negative 3rd, 6 is 10 to the negative 6, so the difference between them is 10 to the 3rd, or 1,000. So you would be prone to look at this and say the difference between 3 and 6 is that 6 is double 3. So that ultimately you're going to look and say, all right, 6 is towards neutral, because neutral in this case is 7, that's dead center. 14 is going to be very basic, 1 is going to be very acidic. So if we're looking at this, we're moving towards neutral. So I would say, all right, 3 must be twice as acidic as 6. But that's not true. 3 is actually 1,000 times more acidic than 6. And so that's why it's important you realize how a logarithmic scale works, because you got to understand that going from 3 to 4 here means that you're 10 times less acidic, right? Because 4 is closer to neutral, so I've moved 1 notch, that's 10. If I were to go from 3 to 5, it'd be 100 times less acidic. 3 to 6, 1,000 times, 10,000 times if it's 3 to 7. And the reverse is true. If I go from 6 to 3, I'm 1,000 times more acidic now. So it's very, very important you realize even small changes in pH are actually big changes in pH. Because this is logarithmic, it's not like the difference between 2 and a 1 is just a little bit. It's actually a tremendous amount. It's 10 times that difference. And then as we wrap up here, let's just go through and make sure we're clear. So on the scale, you're going to have that neutral's going to be, boom, 7. And so this will be distilled water, pure water. And this makes sense because if we mix acids and we mix bases, you'll notice what we get. Water. So this is how we can neutralize acids or bases, is if we put acids with bases, we just get pure water. So technically, if we did this perfectly, we would just get a bunch of pure water. Now, acids are always going to have a pH below 7, so that means they have more H plus than OH minus. Bases will always be above 7, which means they have more OH minus than H plus. Because keep in mind, if I add a bunch of base, if I add a bunch of OH minus, that OH minus is going to attach to my H plus to make water. So essentially adding OH minus is the same thing as removing H plus. I know it seems kind of weird, you're like, but I didn't do anything to H plus. But you did, because adding OH minus will bind H pluses, so you now have less H plus. So adding bases does actually decrease your acidity, because adding bases makes it where you have less of the H plus that makes you acidic. And buffers are kind of a cool thing biologically, where these guys can oftentimes both absorb H pluses and release them. So based upon the pH, these guys can help balance things out. So these are present in our blood, these are present in our digestive system, where if you eat something that happens to be acidic, you'll know it's an acid because acids tend to taste sour, whereas bases tend to taste bitter. So if you were to eat sour foods, which we like, then you have acids coming into our body, we have to neutralize those. We do that by using these buffers that can, when they see the presence of an acid, they can ultimately absorb H pluses. They can attach H pluses to themselves. And if there's a situation where we become too basic, they can release those H pluses to then go ahead and drop our pH to get it back to where it should be. And so buffers are going to be a critical part to what we mentioned before in the year, which was homeostasis. Because we've already said that our pH is critical when it comes to our enzymes working, which is critical to us living. And so it's very important that we keep all of this balanced. So just quick to show you guys things that are very basic that we use to do cleanup, because they're really good at like messing with stuff, would be things like bleach and soap. You can see are on that end of the spectrum. We also use ammonia for cleaning, although it tends to be a little bit less basic, so it's not quite as dangerous, I suppose, if you get it like on your skin or something, although I wouldn't drink it. It is still toxic. You've got milk of magnesia. This is what you take when you want to get rid of some of the stomach acid. So if you have like acid reflux, you take milk of magnesia, and then that base that's in the milk of magnesia binds to the acid that's coming up from your stomach. It's hydrochloric acid, and it neutralizes it, makes water, and so that way it's not chemically burning your esophagus anymore, so you feel better. Then you've got baking soda, seawater, things slightly basic. Urine, slightly acidic there, not much. Coffee, slightly acidic. But you can see there's things that are fairly acidic that we even drink. You know, you've got tomato juice, you've got orange juice. Lemon juice, we're starting to get to the point we don't. You'll see we drink and we routinely ingest things probably down to around a pH of about 3. When you go beyond there, things like lemon juice can actually do some damage to your teeth because they're acidic enough they can wear at them. So you normally want to start avoiding things as they get close to a pH of 2, although some people like really sour things, so they'll have them in moderation. But if you have too much of them, you can see these things can sometimes cause even sores in your mouth, because they are reacting with the cells and with the tissues in your mouth in a not so friendly way. If you've ever sat down with a bag of atomic warheads that are sour and managed to make it where your tongue bleeds, you'll know what I'm talking about. And then we have gastric acid. This is the stuff in our stomach that helps break down our food that has a pH of about 1. That's why if this gastric acid from our stomach gets up into your esophagus, which isn't protected by a layer of mucus, that's why you get that burning sensation that you might hear called heartburn. That's your esophagus being chemically burned by acid, which is not fun and not that safe, which is why they give you medication to try and treat it, or they make you change your diet.